going to worry about that ideal gas law. Now, we're going to talk about something called ideal gas law. This is ideal gas law is a hypothetical gas, and what that means is basically this gas is how we want gases to behave. So we're going to compare kind of ideal gases and a real gas. And a real gas would be like, for example, nitrogen or hydrogen or oxygen or chlorine or bromine. Okay, well, I shouldn't say bromine, but chlorine, fluorine, neon, argon. It could be any of those gases. That's a real gas. Okay, oxygen in the air right now, the nitrogen in the air right now, carbon dioxide. Okay, those are real gases. We're going to pretend that basically we have this ideal gas. It's a hypothetical gas. So it's not, it could be one of these gases, but we're going to say this is how we want the gas to behave. Okay? So it says here, an ideal gas is a hypothetical gas that obeys all gas laws perfectly under all conditions. And we're going to talk about that real soon here. So this ideal gas, it's going to obey all the gas laws under all conditions. That's not true, okay? But we're going to pretend that it does. And it turns out that real gases and ideal gases, how we want them to behave, are pretty close to each other. They're very, very close to each other. But we have to be aware of certain things, okay? So it says here this. Let's just ignore this for a quick second here. Let me ask you something. If we're talking about a real gas, like the gas in the air right now, or we have a gas in the lab or something like that, what happens when you cool down one of those gases? We've talked about this before. What happens when you cool down a gas, whether it's in the air or let's say you got some, or a gas in the lab, what happens when you cool them down? Yep. It turns into a liquid, yes? So it would turn into a liquid. It would cool down enough that we take kinetic energy away from those molecules, right? Because gas molecules have kinetic energy. They're moving past each other. They're sliding, like they're just moving, right? They're bouncing off the walls. They're bouncing into each other. But if we slow them down enough, okay, then we're going to basically take enough energy away so that when they're sliding past each other like this, they're going so slow that attraction between those molecules is actually going to be strong enough to hold them together. Okay? So if we cool them down, we could turn them into a liquid. What it's going to say here is this. An ideal gas would not do that. Okay? Which, again, remember Charles' law? We talked about, he said, okay, at this temperature it has this volume. At this temperature it has this volume. At this temperature it has this volume. And it's this line that keeps going and going. And then eventually it turned into a liquid, yes? And then he stopped the experiment because he said, well, I can't study the volume of a gas and this because it's not a gas. But what we're going to say is we're going to pretend that no matter what temperature we have, it's still a gas. Okay? Again, we're going to stay away from, how do we fix this? Well, easily. We don't study gases at low temperatures, because they don't behave the way we want them to. Okay? So we're going to stay away from low temperatures. We're going to maybe go 0 degrees or 25 degrees Celsius room temperature. Maybe we're going to talk about 70 degrees Celsius or 80. Make sure it's a gas. Okay? So we're going to try and stay away from very low temperatures. This basically says that this ideal gas, if we could come up with this perfect situation, this gas would not ever turn to a liquid, which we know is false. But we're going to pretend that that's the case. And again, it's fine to pretend that because they behave very similarly, only if we stay away from low temperatures. Okay, and we're going to do that. Okay, you're going to see most of the questions are not like negative 400 degrees, negative 300 Celsius or something like that. Stupid. Negative 100 Celsius. We're not going to study gases at negative 100. We're going to stay away from low to negative 50. We're not going to even go into that realm because, again, we start going into that section, we're going to start changing it to a liquid, right? So we're going to stay away from that. You're going to see all the questions are kind of 25, maybe 0, okay, where it's still a gas, but we're going to stay away from low temperatures. Gases, this kind of goes back to Charles' law again. Gases have particles that take up space, yes? Okay, they take up space. We're going to pretend that basically particles have zero size, and we're going to pretend that these zero size particles also do not attract each other, okay? Which again is not true. Real gas does have some size to it, very small, yes, but they do take up a little bit of space, okay? And real gas molecules are attracted to each other. And you can, we know that from the simple fact that we've talked about London forces even, for example, right? I mean, HCl is a gas, hydrogen chloride is a gas, right? We've talked about that one before. In fact, it's even polar. So we know it has a negative end and a positive end, and they're going to be attracted to each other. But the particles are going so fast that they can't hold on to each other, right? That attractive force isn't strong enough to hold them on, to hold them together. So therefore, we know that hydrogen chloride is a gas. But again, if we cooled it down enough, we could probably slow them down enough that those attractions would be strong enough to hold it together as liquid. We stay away from low temperatures. But gases are attracted to other gases. I don't care if you have oxygen in the air right now, right? O2 compared to O2. That's London forces. That's why we talk about Unit 1 first. When they're going past each other, there's going to be an attraction, okay? Is it strong enough to hold them together? No. But there is going to be an attraction there, okay? We're going to pretend that there's no attraction for this, okay? And it basically says this, and this is the important part. Real gases, of course, would condense. They have particles that attract each other, and they do not follow these gas laws exactly, okay? So, what is the difference between a real gas and an ideal gas? We have particles of zero size compared to particles that actually take up space. We have particles that or gases that do not condense into a liquid, whereas we're going to pretend that they don't condense. So, but we know that they do. Okay, and they do attract each other. A real gas does have attractions between molecules. We're going to pretend that they don't. Ideally, what you need to know is this. Okay, real gases deviate most how we want them to behave. So there's the biggest difference if we have low temperatures and high pressures. That's the most important part. Okay? If we stay away from low temperatures, our gas will not condense into a liquid. If we stay away from low temperature, which we talked about already today. High pressure, what happens if you put gas molecules under high pressure and you force them all together? What's going to happen? They're going to turn into a liquid, yes? Okay? So again, we don't want to create a ton of pressure and push all those gas molecules really, really close together because, of course, when we put a lot of pressure on there, the volume's shrinking, okay? Now we're combining all those gas molecules into a tiny little space, and they might not have a choice. They might have enough attractions to now turn into a liquid. Okay. So basically, what I want to say to you is this: if we're going to use the ideal gas law, okay, which is what we're going to talk about today, the formula, we want to stay away from high pressure and low temperature. You need to know that. Okay. And if we do that, then we're fine. Okay. And most of these questions are based on that principle. Okay. That they will not condense. Okay, good. This is the most important thing to know. Okay, we do not want low temperatures and high pressures. We do not want that. Okay, now, under most normal conditions, a real gas behaves very similarly to an ideal gas. And the relationship looks like this. The amount, what letter is that, by the way? Amount. Yeah, N. Okay. The amount can be related to the pressure, the volume, and the temperature by using the ideal gas law. Okay? The ideal gas law, I know that's kind of a little bit small there, but basically it says PV equals nRT. That is what we call the ideal gas law relationship / formula. Okay? Now, there are certain units that go with this. P stands for what do you think? We already talked about it here. What is it? Say it. Pressure. And that has to be in kPa. You do not get options in this formula. Okay? You do not get options in this formula. V stands for what?
Volume.
In liters, has to be liters. Again, if it's in milliliters or kiloliters, you need to convert it. Okay? N is what? Amount, which we measure in moles, yes? We're going to skip R for a quick second here. T is what? What's T? In Kelvin. Okay? Temperature is always in Kelvin, no matter what formulas we're using. Okay? And what they did was they studied the relationship between the pressure and the volume and the temperature and the amount of gas that they had, and they came up with this constant. And so R is something called the universal gas constant. It looks like this. 8.314 is the number. Okay, again, don't Google it. It's on the back of your periodic table. Okay, if you Google it, you're going to get some other crazy, like longer number or shorter number. We need to make sure we're using this one, 8.314. The units that go with this tell you, it's kind of convoluted here, but it's a constant. So we're trying to cancel out the units that we don't need, basically. Okay? So the units that go with 8.314 are liters, kilopascals, moles, and Kelvin. If you ever forget what units you won't, because we're going to do this over and over again, but if you ever forget P equals nRT, what units do I need to have, just you look at the universal gas constant, and it tells you it's 8.314 liters, kilopascals, moles, Kelvin. Those are the 4 units I need to use in this formula. Okay? Could you use, is there a relationship between ATMs here, for example? Could you have a number, or could you have this same relationship with ATMs? The answer is yes, you could. Okay? But we don't do that one, we do kilopascals. The problem is, if you chose to put ATMs here, you'd have to switch this number accordingly. Okay? You could, but we're not going to. Okay? So the answer is, yeah, there's a relationship between any pressure, any volume. The temperature still has to be in Kelvin. The moles is going to be the moles. But you could switch those units for pressure and volume if you switch the universal gas constant, but this is the only one we're going to give you. Okay? So make sure you're using the appropriate units, basically. Yeah. Yeah. Okay? The universal gas constant can also be compared. Look, if you look at P equals nRT, another formula I think about is this one here. Again, N equals little m over big M, right? We're probably going to have to use that at some point as well, because we need to make sure that we are talking about, if I give you the mass of the gas, we need to figure out the amount of that gas. Okay? So we want to make sure we have that there as well. Okay? So between those two formulas, that's what we're kind of looking at today. Kind of a combination of those two things. Good? Okay. All right. So we have a couple questions to go through here. So let's take a look here. It says, what amount and mass of hydrogen gas, 45 liters, 75 kPa, and 290 Kelvin. Okay, so again, what I would suggest doing is going through, labeling what we need to find. What amount? What letter is that? N. Mass? Little m. Hydrogen gas, what does that look like? Sure. Big M. And what else? Hydrogen gas, while I'm at it though. H2. Yes. Hydrogen gas. H comes in twos. I have no very clever friends. People stupid. Okay. What's V? What's V here?
45 liters.
Yeah. And what's 75 kPa? Pressure, and add 290 K. Okay. So there you go. Okay. So it looks like I have the pressure, I have the volume, I have the temperature. I'm looking for the N, the amount, and I need mass and molar mass, of course, as well. Okay? So what amount? That's the first question. I guess I'll start with a little PV equals nRT. And I guess at some point, if you want to, you can also write down the other formula. N equals mass and molar mass, right? Like that there, for example. Okay? Well, it says what amount. So I need to solve for N. I could try to solve for N here, what amount, but the problem is I only know that the molar mass is 2.02 grams per mole. I don't know what the mass is, or sorry, I don't know what the mass is, right? So that's not going to help me there. And I can't solve for amount there because I don't know enough information. So I'm going to go back to here. What letter should I solve for here if I want to find the amount? Yeah. Okay, so I'm going to divide by R and T. Yes. R and T. And I'm going to divide by R and T here. Yes. Okay. And to find the amount, I'm going to use P, B, R, T. Okay. R, by the way, is 8.314. I'm going to be honest with you. I'm usually not going to write down the units there. If you want to, by all means, you probably should. It's, what did I say? Liters, kilopascals over moles Kelvin. Okay? Liters, kilopascals over moles Kelvin. What's the pressure? I said 75 kPa. That's going to go here. I do want to write down the units here. The volume is what? 45 liters. R, 8.314, universal gas constants on the back of the periodic table. And the temperature is 290 K. Now, again, when you go to do this, please make sure that you use brackets accordingly. Okay? Now I'll move it over here. The pressure was what? 75 times 45. And again, if you want to get an answer for that, that's fine. Hit enter. Or put that in brackets on the top, whatever you want to do. But the most important thing is that we take 8.314 and multiply it by 290 here. And put that bottom part in brackets. If you're going to do this all in one step. Or do the top, then do the bottom, and divide those two numbers. That works as well. You cannot round them. Okay? Or put the bottom part in brackets. You should get 1.399.
Does R have like
They have multiple units. Liters, kilopascals, moles Kelvin. Okay? Now, there's two parts to this question, so just be a little bit aware here. I put down 1.399 moles. The question says what amount. So I want to get an answer for that. So I want to go back and actually record it. It's like that's part A of this question, if you want to think of it this way. So I want to write down a number for that, or basically an answer. So what amount? I'm going to look at my units here, or I'm going to look at my significant digits, and I see there's 2, 2, and 3 in my question. So I probably should have 2 in my answer. So I am going to put down here 1.4 moles, and I'm going to circle it. That's the amount. Okay. And is that okay? Good. Now I need to know, it also says, now second part, or part B of this question, even though there's not A and B, it says what's the mass and the mass. So that's the second part of this question. Well, how am I going to find the mass? Well, now I have enough information, right? So I would say, well, instead of trying that, I would say, hey, let's find the mass. So I'm going to use this formula instead, N times big M. And I have the moles now. But remember, we need to use the unrounded number here, yes? Okay. We're not going to take the 1.4 because we rounded that. That was my final answer for that part of the question. But now I want another part of this question, and so I don't want to use the rounded number. Okay? So I'm going to use 1.399, yada, yada, yada. And we're going to multiply that by 2.02 grams per mole, molar mass, H2. Okay? And that should work out to be, if I'm not mistaken, all said and done, 2.8 grams. Again, 2 significant digits. Okay? And that number is on your calculator, so all you have to do is go that times 2.02. There you go, 2.8. Okay? Like so. Good? Okay. That's one example of kind of what you'd see today, roughly. And again, you might just be asked to solve for the amount. You might be solving for M. You might be solving for T. Probably not R. You could be asked to solve for R. You could. Why not? You could solve for R and see how far away you are from 8.314, because we know it should be 8.314. So we could solve for R and see, you know, does this gas actually behave the way we want it to, or whatever, kind of compare it. We could definitely do that. Okay, good. Questions, anyone? Okay, let's go to the next one here. And everyone's got that good there. This one says what pressure would be exerted by 50 grams, which is the mass, oxygen gas. I can get the molar mass, and oxygen gas looks like that. There's my temperature, and there's my volume, right? So go through again. I would strongly suggest you go through and label those variables, okay? Now, before we go any further, just give me 1 second here and pay attention, please, okay? Now, we kind of have, I wouldn't say we really have another formula for this stuff. These are kind of the two main formulas that we're going to talk about for the most part in this unit. How do you know which formula to use? Do I use P1, B1, T1, P2, B2, T2, or do I use P equals nRT? How do you know? When you read this question here, how do you know you got to use this formula and not the one from yesterday, combined gas law? Combined or idea? How do you decide? Abby? Right. Yeah. If you look up here, what pressures are you going to compare? Right? What volumes are you going to compare? What's the temperature you're going to compare? You can't, right? There's only a pressure and there's a volume and there's a temperature. And also you'll notice that this one talks about grams, yes? And the other one, yeah, the last eight didn't. It was just pressure, volume, temperature. That's it, right? So you got to be able to, because your quiz on Friday is going to have this, where I'm going to throw a couple of each in there, kind of thing, and you have to decide what kind of formula do I use here. Do I use P1, B1, T1, combined gas law, or do I use the ideal gas law? Okay, and it depends obviously on the information you're given. Are you comparing initial conditions to final, or are you just trying to find the pressure of the gas or the temperature? Excuse me. Or the mass of the gas or something like that, okay? This one asks you to find the pressure. So let's take a look. Pressure, PV equals nRT. I'd probably go with that formula because, again, I don't have two pressures or volumes or temperatures to compare. If I want to get the pressure by itself, I divide by V, and I divide by V. So I'm going to have to do N R T over V. And R, by the way, is 8.314. So I'm going to throw that in right now. We have 50 grams. Where does 50 grams go in this formula? Where does 50 grams go in this formula? Where? Yeah. Trying to find the amount. Is it N? No. Okay? So you're going to have to do that separately. That's where this little formula is going to come in, right? Over here. 50 grams over the molar mass of oxygen, which is 32 grams per mole. And I believe that is, help me out here, I think it's 1.5625, is that right? Does that sound right to anyone? Yes? I'll double check it right away here. 1.5625 moles. Now that's N, okay? I can clearly, I know pretty darn quick who has a good grasp of this and who doesn't. Because when I see people put 50 grams into this part right here, then I know we don't know the difference between mass and moles, right? And that's a problem. So we're going to put in our 1.5625. I hope that's the right number there, moles. What temperature do I need to put in there? Yeah. Yeah. So it's 313.15 Kelvin, I think. Okay. Convert it to Kelvin. And then the volume is what? 100 liters. Again, if that was in milliliters, you got to convert it to liters. So you have to be able to change between milliliters to liters and liters to kiloliters, et cetera, et cetera. But everything has to go to liters. Okay. And let me just check that real quick here with some good old calculator stuff. Okay. So we got, what did I say? 50 divided by 32. 1.5625, that looks good. I'm going to take that and times it by 8.314 and times that by 313.15, and we're going to divide that by 100, and that's 40.68, right? Well, I'm going to have to use some significant digits here. So 40.68. Let's see here. What do I got? 3, 3, 4. So I can only have 3. So 40.68 would be 40.7 kPa. Okay? Should be my final answer. Good? Questions, anyone? Okay. Those are two kind of quick examples. That's basically what we're going to do today. Again, you could solve for any of these variables. You could solve for P or V or N or R or T, mass, molar mass. You can solve for any of them. Okay? If you don't know the molar mass of a certain gas, for example, but you're trying to find it, you'll have enough information to do that. Okay? So you'll just have to solve for big M eventually, which of course is mass over moles. Okay? So we'll do that right away. Well, anyway, yeah, that could be an option. Okay? So you could solve for any one of these variables, absolutely. Okay? You could solve for R, like I said, probably not, but you could. And then you could compare to 8.314 and see, what's the percent yield or percent error stuff, which we'll talk about someday down the road. Okay? But we could do that too. All right? Any questions on that? Anyone? Sure? Okay. All right, well, I'm going to give you a worksheet here for that, and let you guys work on that for a bit.